So we're coming to the end here, section 14.9, talking about pH and pOH. And I'm pretty sure most of you have heard of pH, right? So we use pH as a way to express acidity and basicity. If the pH of something equals 7, that's a neutral solution. If the pH is less than 7, it's acidic. If it's greater than 7, it's basic. And so here's a chart, neutral being in the middle. Low pH is very acidic. High pH is very basic. But what exactly is pH? It's a logarithmic scale. And we sometimes, what did I do? We sometimes use logarithms to help compress something that's scattered over a wide range. The concentration of hydrogen ion can vary by 14 orders of magnitude. So if you're trying to graph it, it's like impossible because there's just no way you can do that. So we use a logarithm. And so if we look at a hydronium or a hydrogen ion concentration of 10 to the minus 4, and that's molarity, we find that the pH is 4. 10 to the minus 3 is a pH of 3. 10 to the minus 2 is a pH of 2. Do you see a relationship there? The pH is the exponent on the 10 made into a positive number. 10 to the minus, if we have 10 to the minus 4 being represented as one circle, 10 to the minus 3 concentration is 10 times as much, and 10 to the minus 2 is 100 times as much as this. Because these are factors of 10. It's increasing by factors of 10. And so it gets really, really big, really, really fast. And the logarithm helps to kind of condense that. And so we see that there's a change from 4 to 3, that's an order of magnitude, and from 3 to 2 is an order of magnitude. Now I'm blanking. The scale for earthquakes has a name. Richter scale. The Richter scale, where they rate earthquakes, is also a logarithmic scale. And so the difference between 6 and 6.1 is not very great, but between 6 and 7 is huge. That's 10 times stronger earthquake. So it's a similar idea. So pH, this is the definition of pH, and this is something you're going to want to write on your note card. pH is negative log of the hydronium ion concentration. This negative here just means change the sign. It's not anti-log, okay? It's just the logarithm. So let's look at logarithms for a minute. Let's see if I remember what I was going to do here. It's just a nice blank slide. Okay, so the log of 10, actually let me do this way. So here's the number, and here's the log of that number. Oh, let's just start completely over. We'll call this x, and over here, this is the log of x. So if x is 10, the log of x is 1. If x is 100, the log of x is 2. If x is 10,000, the log is 4. 10 is 10 to the 1. 100 is 10 to the 2. 10,000 is 10 to the 4. Taking the log of something just asks, what power of 10 is that number? And it's easy to understand when we're dealing with nice round numbers like 100 and 1,000,000 and things like that. If we talk about 500 or 50, like if we try to find the log of 50, we can't do that in our heads. But we can look and see that, well, 50 is between 10 and 100, so the log of 50 must be between 1 and 2, and we can get our calculator. You should get your calculator out because you're going to need it. So if I put in 50 and press the log button, I gotta find it. There it is. The log of 50 is 1 point, let's round that, 1.70. So the log of 50 is between 1 and 2 because 50 is between 10 and 100. This means that 50 is equal to 10 raised to the power of 1.7. We don't often think of exponents as being non-integer numbers, but they can be. If we have a small number, like say 0.001, that's the same as 10 to the minus 3, and the log of that is negative 3. So try these on your calculator. Put in 10 and press the log button. No, I pushed the wrong button. That doesn't help. Press the log button. You should get 1. Put in 100. Press the log button. Does it work? So that's what a logarithm is doing. So let's look at some other numbers. Let's look at, let's try 2.8 times 10 to the minus 4. So put in 2.8 times 10 to the minus 4 and press the log button. And I'm getting minus 3.55. So here's x and here's log of x.
Say how you input it again, because would I go with the log first, log 2.8?
It depends on what kind of calculator you have. I think with yours you need to press log first. The TI-30XA, you put the number in first, and you have to use your scientific notation correctly, otherwise it will give you the log of part of your number. On other calculators, you may have to press the log button first, and it'll show you an open parenthesis, and then you put the number in and press equals. So you need to learn how your calculator wants you to talk to it. And then, so try 2.8 times 10 to the 4, and then try 2.8 times 10 to the minus 9. And that'll be minus 8.55. I should get out my real calculator. Your calculator's cooperating? It's not the user, it's the calculator. It's always the calculator, and we'll have to just speak to it strongly. So look at these numbers, and look at these numbers. What's the same about minus 3.55 and minus 8.55? The 0.55 part. And what's different is the 3 and the 8. What's the same between these two numbers? The 2.8. And what's different is the exponent. When you take the log of a number, this coefficient part shows up after the decimal point. So 2.8 is related to this 0.55. The number before the decimal point is related to the exponent. This amounts to a decimal holding number. If I wanted to do 2.8 times 10 to the minus 13, it's going to be minus 12.55. Because this number is one less than that number. This minus 12.55 is between minus 12 and minus 13, right? It's in between. And this is between 10 to the minus 12 and 10 to the minus, 10 to the minus, yeah, this is between 10 to the minus 12 and 10 to the minus 13. So the reason I'm showing you this is because I want to tell you about how significant figures work with logarithms. Not because I'm going to test you on it, but because I think it's something that a lot of people don't understand, and even instructors that I've encountered don't know how logarithms and significant figures work. The significant figures in this number are the 2 and the 8, right? And those show up over here as the 5 and the 5. Now, when you do this on your calculator, it shows you more digits than the 5, 5. This number out here corresponds to that number. The 4 is not a significant digit. The 3 is not considered a significant digit either, because it just reflects the place holding, okay? Because the only difference here is that the numbers before the decimal point, those correspond to the factors of 10. They don't correspond to the significant figures. So you look at the number you're taking the log of, you say, oh, it's got 2 significant figures. That means when I express the log of it, I should have 2 decimal places. I'm not going to test you on that, but I'm going to use that. And so if you're wondering, why are you rounding it that way? That's why. Okay, any questions about the idea of logarithms or how to get your calculator to give you the correct answer?
Will they expect on the homework to round up, or will it correctly go in this?
I believe on the homework they'll probably tell you how many digits to give, how many significant figures. A lot of times recently they've been doing that. They say express your answer to 2 significant figures or 3 significant figures. And so then just the 3 digits. Okay, so we see that when we have a small number like this that's less than 1, the log of it ends up being a negative number. Negative numbers are difficult to deal with. And so in this pH expression, pH is the negative log. So if this was, now instead of being X, if this was the hydrogen ion concentration, and we want this to be the pH, these are the logarithms. pH is the negative logarithm, so we're just going to make those positive. We're just going to change the sign. That's all the negative means. Take the log of it and change the sign. Now, in some of your calculators, you have to put the negative sign in first and then logarithm in the number. So let's do some examples. Calculate the pH of each solution. Remember, pH is the negative log of the hydrogen ion concentration. So pH equals negative log hydrogen ion concentration. Or hydronium. Remember, we said they're equivalent. So this is negative log of 9.5 times 10 to the minus 9. So this is going to end up being 8 something. So 9.5 EE minus 9 logarithm, change the number, change the sign. pH is 8.02. So do this on your calculator. Because there will be some questions about this on the final exam. And you'll have your note card and you can write this formula down. But if you can't get your calculator to give you the right answer, it doesn't do any good. Anybody need me to speak to their calculator? I got Andrew to put his clothes on this morning, so I can get your calculator to behave. So the question is, why does it say H3O plus over here and I wrote H plus over there? Because I'm lazy. Okay.
Because they're interchangeable.
They're interchangeable. This implies that a hydrogen ion, which is just a proton, is floating around in solution by itself like a 3-month-old baby wandering around Disneyland. Not happening, right? We understand that it is actually riding on a water molecule. So this is more accurate. This involves more writing. And so I did that kind of on purpose to just remember they refer to exactly the same thing. It's a very good question. Any other questions? There's a negative here because when you take the log of this number, it ends up being minus 8.02. And this negative sign tells you have to change the sign. So you have to change the sign, and it should always end up being positive. Let's do this next one. So the pH is negative log of 6.1 times 10 to the minus third. Should be 2.21. Once you learn how to talk to your calculator, this calculation is very simple compared to some of the other things we've done. I was like, yeah, what? This is nothing. Why are we practicing this? Well, you just, you got to do it a couple of times so that you remember next time. So any questions? Everybody's calculator's cooperating? It's good. What if we're given the pH and they ask us for the hydrogen ion concentration? Well, we'll get this equation. The hydronium ion concentration is equal 10 to the minus pH. 10 raised to the power of negative pH. Do you want to see why that is, or do you want to just believe me? Well, believe me. Okay. Yeah, if anybody's curious, I can show you how I rearranged that, but yeah, most students are really not that interested. So that's another equation. Write it down on your note card. So let's do an example. How do we use this? Calculate the hydronium ion concentration for a solution with a pH of 8.37. Well, we need to enter drawing mode first. Always a good move. We're just going to use the equation. The hydronium ion concentration equals 10 raised to the power of negative pH. Now, depending on your calculator, you're going to enter this in a different way. On the TI-30XA, so this is 10 to the negative 8.37. On the TI-30XA, you're going to put in 8.37, change the sign. The 10 to the x button is the other function on your log key. So I'm going to press 10 to the x. It's going to show it to me with a whole bunch of zeros. I want to put that in scientific notation. And this concentration is going to be 4.3 times 10 to the minus 9. What my calculator showed me was this. 1, 2, 3, 4, 5, 6, 7, 8, 9. It didn't show me this 3 because there wasn't room in the display. There was room enough for one digit after all those zeros, and so it showed it to me in decimal notation. And so I need to trick it. A lot of calculators like the TI-30XA will allow you to switch back and forth between scientific notation and floating decimal point. And if your calculator can do that, you need to learn how to do that. Otherwise, what you have to do with something like this is figure out what's the times 10 to the, so it's times 10 to the minus 9, and then you need to trick it into showing you the next decimal place. So multiply it by 100 or 2 or 1,000 or something to get it to move over so you can see the other digits. There are digits there. Somebody had a question. How did I put this into my calculator? What kind of a calculator do you have? 30XA? Okay, so type in 8.37 and then hit the change sign button, the little plus minus at the bottom. And then way up at the top, you'll have to do second And over 2 is the log button. Press that, and you should get this guy. And then on that TI-30XA, press second and the number 5, which has SCI on it, and it'll show it to you like this. Any other questions? Yes? Okay, I'll come look at it.
It's beautiful. Not one that's on fire, though.
Okay, so we have the pH scale. Oh, wait, we forgot something. There was more question to that. No, there wasn't. We forgot, and it was the previous one. Never mind, we'll just skip it. pOH,
This
Can we
one goes
just-
on the card, too?
let's just start over. The pOH scale. So this lowercase p can refer to anything, not just hydrogen ion concentration. We can use it to refer to hydroxide ion concentration. Formula is the same. P means negative log of. So pOH is the negative log of the hydroxide ion concentration. There are some fields where they look at the negative log of the calcium ion concentration. So that would be pCa. So you can have the negative log of anything. It says derive the relationship between pH and pOH. Okay. So you may or may not be interested in this, but I'm going to do it anyway. So we know that this is true, right? We learned that. This is Kw. This is the equilibrium expression for the self-ionization of water. The hydrogen ion concentration times the hydroxide ion concentration in any aqueous solution always 10 to the minus 14. So what I can do is I can take the logarithm of both sides. So the log of this and the log of that. And so when you take the log of things that are multiplied, you end up adding the logarithms. So that ends up being the log of H plus the log, and don't bother even copying this down. Just watch and try to pretend you're interested. What's the log of 10 to the minus 14? The log is minus 14. So what if we multiplied all of this by minus 1? I made this negative log and negative log and made this positive. This is the same as pH, right? Negative log of hydrogen ion concentration. So that's pH. This negative log of OH minus is pOH, and that is still 14. So write this one down. That's a handy-dandy equation. The pH plus the pOH always add up to 14. And, you know, if you followed what I did as to how that came about, great. If you didn't, don't worry about it. Okay, so calculate the hydroxide ion concentration for a solution with a pOH of 4.25. Well, how did we do this for hydrogen ion concentration? We said that the hydrogen ion concentration was 10 raised to the negative pH. We can swap anything we want in there for the H. So the hydroxide ion concentration will equal 10 to the negative pOH. It's the same equation. It's the same relationship. So the hydroxide ion concentration is going to be 10 to the minus 4.25. Oh my goodness. So 4.25, 10 to the x, 5.6 times 10 to the minus 5 molar. That's the concentration of the hydroxide ion in that solution. The P is a function, and it can be a function of hydroxide ion concentration or hydrogen ion concentration. The equations and how you deal with your calculator work exactly the same. Any questions? There's no questions, but there's a lot of murmuring. Are we okay to go on? I don't want to leave you in the dust. I'm not getting an answer, so on we go.